Now we have discussed modeling with autonomous equations, so let us do modeling with linear equations. And the scenario that I want you to think about is the following. So imagine a smoking launch in the airport, right? So people are smoking, so which means that the poisonous smoke is flowing in, but at the same time ventilation is removing the smoke from the air. So ventilation basically does the following thing. So there is the inflow of fresh air from outside and the outflow of the mixture of the smoke together with the air to outside. So, and we are going to construct a differential equation that accurately describes this process. So to make things more complicated, we are going to assume that at noon there is the largest number of people, so the most smoke, but at midnight there is the least amount of people, so we have the smallest possible amount, the smallest possible inflow of smoke. So we are going to make the following assumptions, right? So the volume of the air, then we assume that there is the steady inflow of air. I don't know if it is accurate or not, so now I'm purely speculating, but let's say that ventilation does the following, so that it sucks in 10 cubic meters of fresh air per hour. Then the unit of these poisonous stars from smoke are milligrams per cubic meter. Then the amount of stars at every time moment is C of t. So that comes from the smoke, and we assume that it is a periodic function. So with period 24, because time is measured in hours, so the period is 24 hours, and we need to design a periodic function that looks like this. At midnight, it has a point of minimum, then it has maximum at 12, then at 24 minimum again, maximum at 12, minimum, and so on, right? So this would be 0, this is 24, this is 48, and so on. This is 12, this is 36. So then our function would have local maxima at corresponding to noons and local minima corresponding to midnights. Here is an example. I have designed this example so that the minimum value is 0 and the maximum value is 1. Again, I just don't know how accurate this is. I'm just speculating, but let us assume that it is like that. So for this function, the minimum value is 0 and the maximum value is 1. Then the outflow is 10 cubic meters per hour, but the difference is that what is flowing out is the perfect mixture of existing tars with fresh air. Right, so in other words, in general, if we have the amount of tars, then we have the rate in and the rate out. So let us look at the rate in. So the rate in is going to be concentration of tars in the air times the the inflow. The inflow is 10 meters, so let me write it. So C of t was 1 minus cosine of pi t over 12 over 2, measured in milligram per hour, times the outflow is 10 cubic meters sorry, measured in milligram per cubic meter, cubic meters per hour, then cubic meters cancel out, so which means that the rate of change of the tars is going to be measured in milligram per hour, which is correct, right? So the units here are milligram per hour. Alright, so let us look at the rate out. So the rate out is concentration times the outflow, but now concentration is different. So in the rate in, concentration comes from smoking, and it is given by this function C of t. In the rate out, so when air gets out of the lunge, so now concentration is just the existing amount of tars over the volume of the lunge. Right, so the existing amount equals to y, volume equals I think it was 90, right? This was measured in milligram per cubic meter, so that's the existing concentration of tars in the lunge, and the outflow is always 10 cubic meters per hour. And again, cubic meters cancel out. Y over 90 times 10 is y over 9, and then we get milligram per hour. So that's the rate out, but the total rate of change is of course the rate in minus the rate out. So we need to take this minus this, and that's the right hand side of our differential equation, because the left hand side is always dy dt. Alright, now here is the direction field, and of course from the direction field we can see some kind of oscillating behavior, but how does it go exactly is not clear. So let us solve it, and notice that we have a linear equation. So we have the coefficient at y is 1 over 9, and the free term is 5 times 1 minus cosine of pi t over 12. Right, so in order to solve a linear equation we need to find the integrating factor first. So then we multiply by the integrating factor. Now the left hand side is the derivative of the integrating factor times the unknown function. Right, so which means that in order to solve the equation we need to integrate this very scary right hand side. So it has the exponential function and the trigonometric function. So that's basically what we need to find to calculate. Of course I'm not going to do it by hands. I know how to do it, but it'll take probably 20 minutes of my time. So I think you'll believe me if I tell you that I just used Wolfram Alpha and found the exact answer. Well, it looks scary, probably. But now multiplying by e to the t over 9, we get this final answer. So notice that this term plus c times e to the minus t over 9 as t goes to infinity, it just approaches 0. So which means as t goes to infinity, we have the following behavior. So we have this oscillating behavior, because this is a combination of trigonometric functions, so it just goes up and down, plus some term that approaches 0. And that's why what we see here, that all the solutions, even if they begin very far from each other, they kind of drift towards the same curve, the same oscillating curve. The interesting thing is here is, by the way, that you can check it carefully, that the maximum concentration does not happen at noon, and the smallest concentration doesn't happen at midnight exactly. And the smallest concentration of tars is not 0. So the smallest concentration of tars here is about something like around 30, I guess, maybe slightly less than 30. Alright, so that's how we can apply a linear differential equation to model scenarios where different kinds of substances are mixing and kind of flowing in and flowing out.